Hello, welcome to my astronomy blog. Here we talk about basic equipment needed to practically get on with observing the heavens. I chose to purchase a 4.5 inch, that's 114mm conus reflector scope. It came with some basic set of equipment, and you can see there it's 114mm diameter mirror. Focal length 900mm. That means that light is brought to a focus 900mm in 900mm. Basically, light comes through here, through the top of the telescope, down, hits the mirror, bottom there, is reflected back up, and there's a secondary, which is the see better probably through the eyepiece here. That's it, and that's where the eyepiece goes there. You're now looking at the primary there. Okay, it's factory set, so that means that this mirror in my telescope doesn't really have to be adjusted because it's factory set. And also, Conus use special optical coating. It says a special coating, special design coated optics, which preserves it and also improves the actual optical performance of the telescope. Now what I've decided to do here, I've got this in a cell. I've put a little tiny piggyback scope on, because when the telescope comes, it comes with a cheap spotter, which is basically you're supposed to look through this spotter first before you look through a large telescope. It's supposed to have a wide field of view, and when you look through that, what you should see is those crosshairs, as you can see. And the idea is you line up the crosshairs with an object. I tend to use a church spire, which where I live in England is a good landmark. A church spire, a tree, a chimney pot will do if you can't find anything, a tree or a chimney pot. And the idea is you don't have to worry about how the telescope's set up as regards this clockwork mechanism part. All you want to worry about is if you're looking through this spotter, are you seeing the same thing as through the middle of the eyepiece? Because at night time, you know, believe you me, you think objects are like gas giants are huge objects compared to the size of the Earth, but because of our distance from the gas giants that we're looking at, they're very small in terms of size, in the angle that they subtend to the eye. Okay, so why have a telescope? Well, you don't have to have a telescope to start with. I started with binoculars, and you can pick up binoculars second-hand shops and things like that. I mean, I'm quite a strong physically person, so the only trouble you've got these binoculars, these old-fashioned ones, are very heavy. It's easier if you can put binoculars onto a very simple tripod. The simplest tripods you can get, like, let's go over to one there, which is like so, and basically there'll be a little screw there. And if I move this tripod set away here, set this up. Okay. There's my tripod there, and binoculars have got clamps. They can come with clamps. Don't all come with clamps, but you can actually set a binocular up on a tripod. This one here, which is a very old pair of binoculars, hasn't got one on it. But basically, devices come. You can buy devices that fit at the front of binoculars there, where you can clamp binoculars to a tripod. Otherwise, I'm afraid you just have to put up with the weight of binoculars. They're heavy. So some people observe the sky from deck chairs. It's actually better for your neck if you can actually lie down. An actual deck chair, such as you would find on board a ship, is the best for looking at the sky, because that way you're not straining your neck. And I can't emphasise too much talking about health and safety. I'll just briefly mention it. Never ever look at the sun. If you do, you can blind yourself permanently, and there'll be nothing they can do for you in casualty, basically, because the sun has deadly rays, not just light rays. It contains ultraviolet short wavelength rays that can penetrate the Earth's atmosphere and basically will burn out the rods and cones in your retina, and they will not heal. So I never use a telescope to observe the sun. If there is something like an eclipse of the sun happening near you, as happened in England in 1999, some newspapers will give free eclipse glasses, but they warn you that they're not liable for your eyes. And they're also dated. In other words, the filters have got chemicals in them, but after a certain date, those chemicals will break down. So here we have a scope I got fairly cheaply in a discount supermarket, which is piggybacked. It's a spotter scope, and that one's made by Optus, which is a German company, and this one says it does 20 to 60 times magnification, and it's telling me that the diameter of the front lens is 60 millimeters. The red spot is from my video camera. Now, what does all of this mean? Well, basically, if you want to do astronomy, you start simple. Use your eyes first off. Move to binoculars first. These binoculars, most ideal would be 10 by 50. They're actually 20 by 50 with a field of degrees. That's how much sky you can see, of 3 degrees. If you're strong, if you're quite physically strong, then yeah, they're good, and they'll give you medium magnification. Better than a 20 by 10 would be better than a 20 by 50 would be a 10 by 50 or a 7 by 50. It's not about magnification. Astronomy's got nothing at all to do with magnification. It's to do with light gathering. Here we have a more suitable set of binoculars for a beginner. These are a cheap one made by a company called Miranda. They're 10 by 50, and they will be lighter than the ones that I use at the moment. But like I say, I just quite like using the heavier ones. Just got used to it really. The other thing you probably will need is some sort of flashlight. I use a rechargeable LED. It's better if it's red, because when you go outside it takes at least 20 to 30 minutes for your eyes to get what's known as dark adapted. That is when your eyes are receptive to the much lower light levels, and that's when your eye itself becomes dark adapted, because your retina contains light sensitive cells, rods and cones, and in the dark it's the rods themselves which are you want to be working, and they work better in the dark. The cones are the nerves sensitive, which are more sensitive to colour. Right, so this is my basic setup. You also should know something about where you live. In other words, you're going to have to look up like the GPS position of where you live. Where I live, this is rough, it's about 52 degrees north of the equator, 1 degree west of the Meridian, which is this imaginary line that runs through Greenwich of the time zones. So that means 15 degrees equates for an hour in time in longitude, and the Earth obviously being split into zones of time zones. So I'm already 1 degree west. If I was 7 degrees west, I'd be nearly half an hour behind Greenwich, even though my watch is set to the same time as people who are working in London in Greenwich. I am a seventh of that, which is about 4 minutes. So I'm about 4 minutes, probably from where I'm, probably just over 4 minutes behind. So that means, even allowing for the more complicated equations in science, such as the equation of time and also other factors that come into time, where I live in England, is 4 minutes behind Greenwich, which means to say that the sun hasn't reached the meridian yet, when it has already at Greenwich. If that sounds complicated, I'll show you a little equation I've just had a look at myself before I did this blog. It's called the Equation of Time, where it's very rough. This basically, I discovered that clocks and sundials are related by something called the Equation of Time. But the whole thing, if we go back to basics, just to explain by this diagram underneath, basically if you take the middle, or here is the sun there, and going around the sun, that would be the Earth and the Moon. In this case, it's not a circle; it's actually an ellipse. And on the left-hand side there, I showed that we're actually closer to the sun, the Earth and Moon system, and moving faster. And on the right-hand side, we're further away from the sun, but moving slower. But the planetary laws, which were worked out by a number of scientists, including Johann Kepler, he worked out that, however, the Earth-Moon system sweeps out an equal area of time as it goes around. So, if you like, if you were cutting a pie up that had this shape, this elliptical shape, he deduced that if you cut a slice like so, you'd have to, and you would have moved from this point to that point. But equally, if you had a slice which was more narrow, you'd have only moved from there to there. So that's what he means. What he means to say is that it's sweeping out an equal area. So that slice of cake will be the same size as that slice of cake. That's one of the planetary laws that Johann Kepler worked out. I like to think simple in terms of cake and easy things that I can understand. But also, if you could normally observe downwards, if such a thing exists in the universe, we appear to be going anti-clockwise around the sun. But it's more complicated than that, because the actual axis of the Earth itself is tilted about 23 degrees. And even more complicated is when we're closest to the sun in England, where I live, at this point in the orbit, you would think that's when it's hottest. Well, I did as well. But unfortunately, you'd be wrong, because at that point the Earth is tilted away from the sun. So even though we're closer to the sun's rays aren't striking us. The amount of radiation per square kilometre is a lot less, because we're tilted away, if you understand. Whereas people who live in the southern hemisphere, on my little diagram here, are tilted towards the sun, and they get their summer. So in our summer, in the northern hemisphere, distance-wise we're further away from the sun, but we're tilted towards it. So that's another complication in the equation of time. And there was also another complication, the fact that the Earth wobbles, the actual, like a spinning top, the actual poles of the Earth wobble as well as we move around. The equation of time is due to two things. It's due to the difference in the speed of the movement around this ellipse that was determined by the equations of planets and how they move around in orbits around the sun or any star in general, but also by the fact that the Earth is tilted on its axis. Those two factors put together represent two sine waves, and if you join the two sine waves together, that's what mathematicians and astronomers and physicists worked out. You come up with this equation of time. The way it works is, if we start here, which is January the 1st, the sun's actually slow, so the sun would read 11:57 compared to a clock or a watch when it crossed the meridian. So basically the sun is slow. A clock's already hit noon, so your town clock's already got bonged noon in your town, but 3 minutes later the sun crosses the meridian, and the slowest point being here, where it would read 11:46. So in other words, it would be like 14 minutes behind the watch. But then by the 15th of April here, the sun's caught up with your town clock and it's bang on time. Okay, and again you can see that there are other discrepancies, and just so happens that today, when I'm doing this blog, is the 3rd of November, and the graph's gone completely the other way. The sun crossed the meridian at 12:16. So if you had a sundial, you would think it was noon, but in actual fact your watch would be reading, your watch would be well behind it, basically, be 16 minutes behind it. And another complication, of course, is the fact that you have something called daylight saving times, and that means that in where I live in England, the clocks went backwards last weekend, wasn't it? They went back, and they go back an hour, and that means that now on my clock, looking at my mantelpiece now, it's reading 7:20.